Good evening, everyone. In the last chapter, we discussed about the electrostatics and we discussed about the charge at rest, right? So, but today in this new chapter, that's the current electricity, we'll be discussing about the charge in a motion, right? Charge in a motion. So, whenever charge moves through some cross section, it develops a current in the conductor, right? So, the current is nothing, it's the net flow of charge, right? Whenever through some conductor, through some cross section, the net current flows through some cross section. Whenever the net charge flows through the cross section of a conductor, we say that there is a current flowing through the conductor, right? So in this introduction of electric current, we define electric current as net flow of charge through a cross section, right, in a unit time, or we define it as rate of flow of charge through a cross section of a conductor. That's what we call as electric current, right? Now the question is what constitutes the electric current? What is the cause of the electric current? Why the current flows or why the charge flows through a cross section, right? We know that we have a battery in this circuit. You can see we have a battery here, right? In these circuits. And this battery is connected to the two ends of a conductor, right? And we know that battery is an important source of potential difference. It means that battery provides the potential difference across the two ends of the conductor, right? And we have also studied that our electric field is nothing, it's equal to minus dV over dr, right? dV over dr, right? So where dV is the change in potential or the potential difference between 2 points, right? Or we can say that whenever there is a potential difference between 2 points, there exists an electric field between the 2 points, right? Or whenever in a space there is a potential difference in a space, then there exists an electric field. If there is no potential difference or there is a uniform potential or the constant potential in a space, then in that case the electric field is zero. So it means that electric field only exists when there is a potential difference between the 2 points in a space, right? So similarly, what happens is that we know that battery is an important source of potential difference. If this battery provides a potential difference across the two ends of a conductor, right, it means that electric field will be set in a conductor. When the electric field is set in a conductor, and we know that a conductor consists of free charge, free electrons, right? Conductor consists of free charge or free electrons, where these electrons are free to move throughout the conductor, right? Throughout the conductor, because they are not bound to the atoms of the conductor. They are free. They are free to move inside the conductor, right? So whenever charge is placed in the electric field, in the external electric field, then electric force acts on the charge, right? And similarly in this way also, because of the battery, the electric field is set, and that electric field exerts electric force on the charge, right? And that charge, when is experienced by the force, starts to move in a conductor, right? They starts to move in a conductor, and that constitutes electric current. So we can say that it's the potential difference which is created between two ends of a conductor. Because of that potential difference, electric field is set along the conductor, right? And because of that electric field, the force acts on the charge, right? And that charge starts to move, and that flow of charge we call as electric current. Now we define electric current as this rate of flow of charge with respect to time through cross section of a conductor. That's what we call as electric current. You can see that here we have connected a battery. This is the battery, right? Connected in a circuit. This is the battery connected in a circuit, and in this conductor, this battery is connected with a wire, right? We call this as connecting wire, right? This is nothing. This is a connecting wire, or we can say this connecting wire is also a conductor, right? This behaves as a conductor, right? And we know that whenever negative charge is placed in some external electric field, the negative charge always moves opposite to the direction of the electric field, because the force acting on the negative charge is always opposite to the direction of the electric field. So it means that this is the positive end of the battery and this is the negative end of the battery. It means this end of the battery is at higher potential, right? This end of this battery is at higher potential. this end is at higher potential, right? And this end of this battery is at lower potential, right? This end of the battery is at lower potential, right? And the electric field is always directed from higher potential to lower potential, right? If the electric field is directed from higher potential to lower potential, it means that this will be the direction of the electric field here in this conductor, right? This is the direction of electric field in this conductor, right? And if this is the direction of the electric field in this conductor, then the negative charge of the electrons are always going to move opposite to the direction of the electric field. That's why by convention we say that the direction of the electric current is the direction of the positive charge. So the direction in which the direction along which the positive charge flows is the direction of the current by convention. Or we can say that the direction of current is always opposite to the direction of flow of negative charge, right? So here in this conductor we have negative charge which is flowing in this conductor. So the direction of current will be always opposite to the direction of flow of negative charge. So in this direction the negative charge is moving, and this is the direction of the electric current, right? So opposite to that is the direction of electric current, right? And similarly we can see that if in this circuit the positive charge moves, right, then the direction of the flow of positive charge will be the direction of the current. So one important point here to note is that by convention, the direction of current is always from the higher potential to the lower potential, right? And charge may flow from the higher potential to lower potential, or it may flow from lower potential to higher potential as well. It depends upon the charge, type of charge we are talking about, right? So if moving charges are negative, the current is opposite to the direction of motion of negative charge. If the moving charge are positive, the current direction is along the direction of the flow of positive charge. So this was about the introduction definition of the current and the direction of current, right? And why the current flows in a conductor. The cause of that current is nothing. It's the electric field developed or set along the conductor because of the potential difference or because of the source of potential difference, right? So let's move on to the next part. So if a charge delta Q crosses an area in time delta T, you can see that we have this conductor, right? This is the conductor here, right? And let's suppose delta Q charge is flowing through this cross-section area, right? Through this cross-section area, the delta Q charge is flowing. Delta Q charge has moved in time delta T, right? In time delta T. Then the current we call it as average current. This is the average current, and this average current is nothing. It is the total charge flow divided by the total time for which this charge has actually flown, and this we call as average current. This is nothing. This is the average current, right? Average current. So average current is nothing. Average current is nothing. It's the total charge flown through the cross section of a conductor for the time delta T, right? So this is what we call as how we define as the current. So current I is equal to delta Q upon delta T, right? But this is average current. And we know the SI unit of the charge is coulomb and the SI unit of time is second. Then the SI unit of current is nothing. It's coulomb per second, right? Current is coulomb per second, or we call it as ampere. So current is also called as ampere, or we can say SI unit of charge is coulomb per second or ampere. It is denoted by a symbol A, right? Symbol A. And 1 ampere is nothing. 1 ampere is nothing. If 1 coulomb of charge flows through the conductor in time 1 second, we say that the current established or the current flowing through the conductor is 1 ampere, right? The current flowing through the conductor is 1 ampere, right? So we have two types of currents. One current we can differentiate, or we can categorize the currents into two different types, right? It depends depending upon the source, basic source of the current, right? And one current we call as direct current, right? Another we call as alternating current. Sometimes we call it as DC, or we call it as AC, right? This is what we call as AC current and the DC current, right? And the source of the direct current is nothing. It's the battery, right? And for the alternating current is the generator, right? Is the generator. Let's try to understand what actually the direct current mean and what actually the AC current is. So direct current is nothing. It's the constant current flowing through the circuit, right? Neither the magnitude of this current changes nor the direction of this current changes. It's a current of constant magnitude in direction as well, right? So we can represent the direct current with this graph here. If we plot a current versus time graph here, so this will be the plot for DC current. Here in this case, we can see that neither the direction of the current is changing, nor the magnitude of the current is changing. So we call this as direct current. Similarly, if we see in the next second graph here, if the current is changing like this in case of AC generators, right? In case of AC generators, and we can see, we will learn it in the next chapters, right? When we study about the alternating current and EMI as well, then we will see how this alternating current is actually developed using the generator, right? But what happens here is that you can see at different times, the current or the magnitude of the current is different, right? Or you can also see that the current increases and becomes maximum after some time and then starts to decrease, right? And becomes zero at some point, right? Let me call this as time t naught. At time t naught, this current becomes zero, and now this current starts to increase again, but in the negative direction. So it means that here the direction of current reverses. Direction of current is reversed or changed. So in this case, we can see the magnitude of the current is also changing, right? Magnitude of the current is also changing, and the direction of the current has also changed after time t equal to t naught. So this type of current we call as AC current or alternating current, right? AC currents or alternating current. So this is the basic difference between the DC current and the alternating current, AC current. So in case of DC current, there is no change in the direction of the current, but in case of AC currents, the direction of current changes after some time. And this AC current we see in AC generators, right? So we'll be studying the AC generator in alternating currents, right? So this was the basic difference between the DC and the AC, right? Let's move on to the another part of this electric current. We define two types of current. One is the average current, another is the instantaneous current, right? We define this average current is nothing, I average, right? Average current is defined as, it's nothing, it's equal to the total charge flown upon the total time. So total charge flown upon the total time is nothing, it's the average current. This is how we define the average current. It means that if delta Q is the total charge, right? And it has flown in a time delta T, right? And this delta T time is a significant time, right? Delta T time, right? Then the average time or the average current we can define as, that's nothing, that's I average, that's equal to delta Q upon delta T, right? So this is the average current, right? This is how we define the average current. So average current is nothing, the total charge flown through the circuit or the total charge flown through the conductor in delta T time, right? Now let's suppose if delta T, this time is very small, right? It's an infinitesimal time. If delta T tends to zero, right? If delta T tends to zero, then current I will be defined as limit delta T tends to zero, right? Delta Q over delta T, right? Then it will be nothing. It will be the dq over dt, right? And this current we call as instantaneous current, right? Instantaneous current. So instantaneous current is different than that of average current, right? So instantaneous current is nothing. It's the rate of change of current with respect to time, and we can calculate the current at any particular instant, right? By taking the derivative of time, derivative of charge, which is as a function of time. Then at that particular instant, we can calculate the how much current how much current is flowing through the circuit. So this is what we call as instantaneous current. So we can say the instantaneous current is nothing. It's the current measured at some particular instant of time, and it is calculated as first derivative of charge with respect to time, right? So let's try to understand some of the fundamental things about the current. So current is a very fundamental quantity, right? It's a very fundamental physical quantity, and having the dimensions will be nothing. It will be M0, L0, T0, and A1. So this is the dimensional formula of current. And one more important point about the current is that it's a scalar quantity, not a vector quantity, right? So the direction of the current is very important, right? Even if the direction of current is very important, but still it's a vector, it's a scalar quantity, not vector quantity, because the current does not follow vector law of addition. Do not follow vector law of addition, right? Do not follow vector law. Because we can see that, let's suppose that if we have two sources of current here, one is 2 ampere here and another is 3 ampere here, and this is the final conductor here, right? Then 2 ampere and 3 ampere, they are at an angle of theta, right? But if we see, if we measure the current flowing through this wire, this will be nothing. It will be 2 plus 3. That's the normal algebraic sum of 2 ampere and the 3 ampere. That's equal to 5 ampere. It means that it does not follow the vector law of addition, right? It does not follow the vector law of addition. It only follows the normal algebraic addition, right? So that's why we say that current is a scalar quantity, not a vector quantity, right? So current is a scalar, not a vector. And the direction of current is in the direction of flow of positive charge, or we can say that it's against the direction of flow of negative charge, right? And one more important point about fourth point about the current is, or charge time graph is, let's suppose we have been given some charge versus time graph, right? This is like this, right? Then the slope of this charge time graph is defined as dq upon dt, right? Or we can write it as tan of theta also, right? So this slope gives us nothing. This slope of charge time graph gives us the current flowing through the conductor or instantaneous current, right? If the slope is a constant, then the current is constant. If the slope is varying, then the current is also varying, right? And the area under and the area under current time graph, if we have current time graph like this is the current time graph, IT graph, right? If this is the IT graph like this, then the area under this IT graph gives nothing. It gives us the delta Q charge. It means the total charge flow. So area under current time graph gives us the charge flow. So there are two important points here. Three important points basically. One important point is that current is a scalar quantity. Another point is that the slope of charge. The third important point is that area under current time graph gives us